Infinity is not the biggest thing there is. It is not even one thing. Take the sliver of numbers between 0 and 1. The gap so small you would never bother to measure it. And it holds more numbers than all of counting put together, stretching out forever in every direction. You were raised to think infinity is the end of the line, the one endless thing, the place where counting finally runs out and there is nothing past it. It is not. There is a smallest infinity and then a larger one, and then a tower of them climbing forever with no top floor, and the man who first proved this was right about every single step, and they destroyed him for it anyway. Tonight I want to walk you slowly and carefully through a 3-page paper from 1874. A teacher named Kronecker, who called him a corrupter of youth. A single question that sat first on Hilbert's list of the century's great problems. And 2 men, Gödel and Cohen, who proved decades after his death that the question has no answer and never will. If you are new here, welcome to Fault Lines. Settle in, get comfortable, and subscribe if you have not already. Because the simple question you think you can answer right now, how many points sit on a line, is about to turn into a question that mathematics itself refuses to settle. Stay to the end, because by then you will not be able to tell where the proof stops and the faith begins. Let's ease into it. Take the numbers between 0 and 1, just that little sliver. The part of the number line so small you would never bother to measure it, the gap between nothing and barely anything. There are more numbers hiding inside that sliver than there are whole numbers in the entire infinite universe of counting. More than 1, 2, 3, 4, going on forever in every direction. Not more as in a bigger pile of the same stuff, more as in a different kind of endlessness, a larger infinity, a size of forever that the ordinary forever, the one you learned to count with as a child, can never reach, no matter how long it counts, no matter how many billions of years you give it, no matter how far past the heat death of the cosmos you let it run. It will never catch up. It cannot catch up. The gap between those 2 infinities is not a gap you can close. It is a wall. That is not a riddle. That is not philosophy. That is a theorem. It was proven in 1874. It has been checked by every competent mathematician alive for 150 years, and it is as solid as the statement that 2 + 2 makes 4. There are different sizes of infinity. There is a smallest one and then a bigger one, and the bigger one is so much bigger that the smaller one is, in a precise and provable sense, nothing beside it. And the man who first saw this, the man who dragged it out of the dark and wrote it down and showed it to the world, was called a charlatan. He was called a corrupter of youth. His work was described by one of the most influential mathematicians in Europe as a disease. He was blocked from the job he wanted for his entire life. He suffered breakdown after breakdown, and he died in 1918 in a psychiatric clinic in the German town of Halle, malnourished, half-starved by a wartime food shortage, writing letters begging to be allowed to go home, while the discipline that would later call his work the finest achievement of the human intellect looked the other way. That is the story you have probably heard, if you have heard any version of it at all. The mad genius who stared into infinity, and infinity stared back and broke him. It is a good story. It is the kind of story that gets told at dinner parties by people who want to sound deep about the dangers of thinking too hard. It is also wrong, and the way it is wrong is worse than the legend, not better. Because here is the thing nobody puts on the poster, the thing he was actually chasing at the end, the question he kept returning to through every manic high and every crushing collapse, the problem he was convinced God himself had handed to him to solve, turned out to have no answer. Not no answer yet. No answer ever. Decades after he died, two of the greatest logicians who have ever lived proved, separately and conclusively, that the specific question George Cantor spent the back half of his life breaking himself against is one that mathematics cannot answer. Not because we are not clever enough, not because we have not found the trick, because the answer is not there to be found. He spent 30 years pounding on a locked door, and long after he was in the ground, we discovered that the door does not open onto anything at all. This is not a story about a man who looked too far into the infinite and lost his mind. The history does not support that, and we are going to take it apart, piece by piece, because the real story of his illness is more uncomfortable than the myth. This is a story about a man who found something true, something that is still true, something that sits underneath every equation and every measurement and every line you have ever drawn. And who was right about all of it? And who was destroyed anyway? And it is a story about the question at the very center of his work. A question so simple you can explain it to a child, that we now know can never be settled. A question about something as ordinary as a line, about how many points are on it. You think you know how many points are on a line. You think the answer is obvious, or at least that the answer exists, even if it is some huge number you cannot picture. I am telling you that there is a precise sense in which that question has no answer, and that this is not a temporary state of ignorance. It is a permanent feature of mathematics itself, and that the universe of numbers will refuse to tell you which answer is correct, no matter how you ask. The line you are imagining right now keeps a secret about its own structure, and the secret is that there is no fact about it to keep. I am getting ahead of myself. I want to get ahead of myself because I want you to feel the size of where this goes before we walk there slowly. But we have to walk there slowly because every step is stranger than the last. And if I tell you the ending now, you will not believe it. You have to be brought to it. Let me take you back to the beginning, to the thing that should have been impossible, the thing that started everything. Different sizes of infinity. Because before Cantor, that sentence was not controversial. It was not heretical. It was meaningless. Infinity was infinity. It was the one, the singular, the endless. The biggest idea there was, and being the biggest, it could not have a bigger. To say one infinity was larger than another was like saying one circle was rounder than another. It was a category error. It was the sort of thing only a confused person would say. And the men who taught mathematics in the 1860s and 70s, the men who built the institutions and edited the journals and decided what counted as real mathematics, mostly agreed on something even stronger. They agreed that infinity was not a thing at all, not a number, not an object, not something you were allowed to hold in your hand and manipulate. It was a direction, a way of saying a process never stops. You could say a sequence goes to infinity, meaning it keeps growing without bound. But you could not say there is an infinity, a finished, completed, endless quantity sitting there, waiting to be counted. The great Carl Friedrich Gauss, the prince of mathematicians, had said it plainly decades earlier. He protested against the use of an infinite quantity as a completed thing, he wrote, which is never allowed in mathematics. The infinite, he said, is only a manner of speaking. That was the orthodoxy. The infinite is a manner of speaking. It is not real. It is not there. Do not treat it as a thing. Cantor treated it as a thing. He picked it up, and he discovered it had structure. To understand what he did, you have to understand the one tool he used to do it, because the whole revolution comes down to a single idea, so simple it feels like a trick. And it is not a trick. It is the most honest thing in all of mathematics. The idea is this: how do you know two collections are the same size if you cannot count them? Imagine you walk into a theater. The lights are low, the show is about to start, and you want to know whether there are exactly as many people as there are seats. You could count the people, then count the seats, then compare the two numbers. That works fine for a theatre, but Cantor was not interested in theatres. He was interested in collections so large that counting them was off the table from the start. Collections with no last member, collections that go on forever. You cannot count to the end of the whole numbers, because there is no end. Counting is out. You need another way. And there is another way, and you already know it. You have just never thought of it as profound. You ask everyone to sit down. If every person finds a seat, and every seat gets a person, and nobody is left standing and no seat is left empty, then there are exactly as many people as seats. You never counted anything. You just paired them up. One person to one seat, perfectly matched, nobody left over on either side. That pairing, that perfect matching, is what mathematicians call a one-to-one correspondence. And Cantor saw that it was the deepest definition of what it means for two things to be the same size. Two collections are the same size, he said, if and only if you can pair them up perfectly. Each member of one matched to exactly one member of the other, with nothing left over anywhere. It sounds like nothing. It sounds like a definition you would skip past in a textbook, but watch what happens when you point it at infinity, because the moment you do, infinity stops being a single smooth idea and starts to crack. Take the whole numbers, 1, 2, 3, 4, on forever. Now take just the even numbers, 2, 4, 6, 8, on forever. Common sense screams that there must be fewer even numbers than whole numbers, because the even numbers are only half of them. You threw away all the odd ones. Half the numbers are gone. Surely, what is left is smaller. But pair them up. Match 1 with 2. Match 2 with 4. Match 3 with 6. Match 4 with 8. Match every whole number, n, with the even number that is twice it. Every whole number gets exactly one even partner. Every even number gets used exactly once. Nobody is left standing. No seat is empty. The matching is perfect. And by the only definition of size that works for infinite collections, the only definition that does not collapse into nonsense, there are exactly as many even numbers as whole numbers. The half is the same size as the whole. Sit with that for a second, because your intuition just got contradicted by an argument you cannot find a hole in. And that feeling, that specific feeling of the floor tilting under a thing you were sure of, is the feeling this entire story is made of. The part is the same size as the whole. Galileo had noticed something like this 200 years earlier and had backed away from it, deciding it just showed that the words larger and smaller and equal did not apply to infinite things at all. He treated the strangeness as a warning sign. Stay away. Here be dragons. Cantor walked toward the dragons, and he found that they had a hierarchy, because if the even numbers are the same size as the whole numbers, he might start to suspect that everything infinite is the same size as everything else infinite. That infinity really is just one thing after all, and the one-to-one correspondence trick, instead of revealing structure, just flattens everything into a single, endless sameness. For a while it looks that way. The whole numbers, the even numbers, the odd numbers, the multiples of 1,000, all the same size. Then it gets worse, because the fractions are the same size too. The rational numbers. Every fraction you can write, every ratio of one whole number to another, all of them packed infinitely densely along the line so that between any two of them there are infinitely many more. You would bet your life there are more fractions than whole numbers. There are infinitely many fractions crammed between 0 and 1 alone, and infinitely many more between 1 and 2. And this is true for every gap between every pair of whole numbers anywhere on the line. It looks hopeless. It looks like the fractions must be a bigger infinity. They are not. Cantor found a way to line up every single fraction in one infinite list, a way to walk through all of them in an order so that each one gets a turn. Each one gets matched to a whole number, none of them missed. The fractions, all of them, dense as they are the same size as the plain old counting numbers. He gave that size a name. He called it the first infinite cardinal, and later he would write it with the first letter of the Hebrew alphabet, Aleph, with a little 0 under it. Aleph Null, the smallest infinity, the size of the countable. There is a way to feel how strange this smallest infinity is, a way that has become famous, and it is worth walking through slowly because the strangeness is the whole point, and rushing past it would be a crime. It is usually told as a story about a hotel, and the hotel is named after David Hilbert, the man who would later stand up and refuse to let anyone expel mathematics from Cantor's paradise. So it is fitting that the clearest picture of Cantor's smallest infinity carries Hilbert's name. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, on forever, one room for every counting number. And imagine that tonight the hotel is completely full. Every room has a guest in it. There is not a single vacancy anywhere in the entire infinite building. Now a traveler walks in out of the dark and asks for a room. In any ordinary hotel, the clerk would turn them away, because full means full. But this clerk does something an ordinary clerk cannot. The clerk asks every single guest to move down one room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. Everyone moves to the room with the next number up. All of them at once, all the way down the infinite corridor. Nobody is thrown out. Everybody still has a room. And room 1 is now empty. The traveler checks in. A completely full, infinite hotel just made space for one more guest without losing anyone. And your intuition about what full means has just quietly died. It gets worse, and the worse it gets, the more it tells you. Suppose a coach pulls up carrying not one new traveller, but infinitely many, a counting number's worth of new guests, one for every whole number, all of them wanting rooms in the hotel that is already full. The clerk does not panic. The clerk asks every current guest to move to the room whose number is double their own. The guest in room 1 goes to room 2. The guest in room 2 goes to room 4. Room 3 goes to room 6. Everyone shifting into the even-numbered rooms. Now every even room is occupied and every odd room, and there are infinitely many odd rooms, is empty. The infinitely many new guests file into the odd rooms, one each, and everyone is housed, the old guests and the new infinity of them, in a hotel that was already completely full before any of them arrived. You can do this trick again with infinitely many coaches, each carrying infinitely many guests, an infinity of infinities of new arrivals. And the clerk can still, with a cleverer rule, fit every last one of them in. As long as the crowd you are trying to house is countable, the full hotel always has room. That is the signature of Aleph Null, the fingerprint of the smallest infinity. You can add to it and add to it and add infinities to it, and it does not get any bigger. It absorbs everything you throw at it and stays exactly the same size. And you would be forgiven, after watching that clerk solve every problem, for concluding that this hotel can house anything, that no crowd is too large, that infinity is simply elastic and will stretch to fit whatever arrives. Hold that thought, because there is one coach the clerk cannot handle. There is an arrival that breaks the hotel completely. A crowd so large that no rule, no shuffling, no clever doubling or tripling of room numbers will ever fit them in. A crowd for which the clerk has to walk out to the curb and admit for the first time that there is no room and there will never be room. We are going to meet that coach. It is carrying the real numbers. But to understand why the hotel fails, you have to see the rest of what Cantor saw first. And here is where almost anyone else would have stopped. Satisfied, having shown that infinity is more subtle than people thought. But ultimately, one thing, all these collections turning out to be the same endless size. Therefore, the natural conclusion, the comfortable conclusion, the one that would have kept Cantor employed and respected and sane, was that everything infinite is countable, that Aleph null is the size of the infinite, full stop. And the strangeness is just that our intuitions about smaller and larger break down out there. But that is not what he found. He kept going to the one collection he had not yet tried to count, the real numbers, every point on the line, not just the fractions, but the numbers in the gaps between them, the numbers like the square root of 2 and pi, the numbers that go on after the decimal point forever, without ever repeating, the numbers that fill the line in so completely that there is no hole anywhere, no gap, nothing missing. The continuum. He tried to line them up the way he had lined up the fractions, and he could not because he was not clever enough, because it cannot be done. And when he proved that it cannot be done, he proved that there is a second infinity, larger than the first, unreachably larger, and that the thing every mathematician for 2,000 years had called impossible was not only possible, but had been hiding in plain sight, inside the most ordinary object in all of mathematics, the line you draw with a ruler. That proof, and what it cost the man who found it, is where this gets dark. He was 28 years old when he found it. It was the autumn of 1873, and George Cantor was a young professor at the University of Halle, a perfectly respectable institution and a complete backwater as far as mathematics was concerned. He had wanted Berlin. Berlin was the center of the mathematical world, the place where the great men were, and Cantor had earned his doctorate there in 1867, and he intended to go back in triumph. Instead, he was in Halle, and he would be in Halle for the rest of his life, and a great deal of what happened to him can be traced to the gap between where he was and where he believed he belonged. Hold on to that, because the man who kept him out of Berlin is about to walk into this story, and he does not leave it. In December of that year, Cantor wrote a letter to his friend, Richard Dedekind, another mathematician, one of the few people alive who could follow what he was doing. The letter is dated the 7th of December, 1873, and in it, Cantor lays out, almost shyly, that he has found a proof that the real numbers cannot be counted, that they cannot be put in a list, that they are, in his careful language, not denumerable. He is not sure of the significance. He half apologizes for bothering Dedekind with it. He does not seem to fully grasp, in that moment, that he has just cracked open the wall that Gauss said could never be crossed, that he has just shown infinity has more than one size. The letter has the tentative quality of a man who suspects he has found something enormous and is afraid to say so out loud in case he is wrong. He was not wrong. He published the proof the following year, in 1874, in the most prestigious mathematics journal in Germany, a publication everyone simply called Krell's Journal after the man who had founded it. And here is the first detail that should make you lean forward, because it tells you something about the world Cantor was operating in. The paper was 3 pages long. It contained the single most important idea about infinity in the history of human thought. And it was given a title so boring, so deliberately small, that you could read it and have no idea anything had happened. The title translates as, On a Property of the Collection of All Real Algebraic Numbers. A property of a collection of a particular technical class of numbers. It sounds like the kind of paper that gets read by 4 people and cited by none. That title was camouflage. Cantor chose it on purpose, and the reason he chose it is the reason this whole story has the shape it has. He was hiding what he had done inside a dull wrapper so that it could get past a specific man. That man was Leopold Kronecker. Kronecker sat on the editorial board of Krell's Journal. He was, by the 1870s, one of the most dominant figures in German mathematics, a small, sharp, brilliant man with enormous influence over what got published, who got hired, and whose career lived, and whose career died. He had been one of Cantor's own teachers in Berlin, and he held a philosophical position about the foundations of mathematics that put him on a direct collision course with everything Cantor was about to do. Kronecker did not believe in completed infinities. That was the orthodox view, and he held it harder than almost anyone. But he went further. He did not believe in numbers that could not be constructed step by step in a finite number of operations, starting from the whole numbers. If you could not build it explicitly, with your hands so to speak, it did not exist. He summed up his entire philosophy in a single sentence that has outlived everything else he ever said. God made the integers, he declared. All else is the work of man. The whole numbers are real, given, divine. Everything else, the fractions, the irrationals, the infinite sets, all of it is a human invention, and a suspect one and the suspect parts should be cleared out of mathematics, like rot out of a beam. You can already see the problem. Cantor's entire life's work was about to be built out of exactly the things Kronecker considered to be rot. Infinite sets, treated as completed objects, different sizes of those infinite sets, a whole tower of them. To Kronecker, this was not merely wrong. It was not a technical error to be corrected in a footnote. It was a kind of pollution of the discipline, a corruption. And Kronecker was not a man who corrected things gently. He was a man who went to war. But in 1874, the war had not started yet, and the camouflage title worked, and the paper slipped through, and the proof that infinity comes in different sizes entered the published record of mathematics wearing a disguise. Therefore, the first great result of Cantor's life arrived not with a trumpet, but with a whisper, smuggled past the border guard, and almost nobody noticed what it was. Let me show you what was actually in it, because the idea is too beautiful to leave wrapped up. Cantor wanted to prove that the real numbers cannot be listed. His later proof, the famous one, is cleaner, and we will get to it. But the heart of all his proofs is the same move, and it is worth seeing once slowly. Suppose someone hands you a list. They claim it is a complete list of every real number between 0 and 1. Every single one in some order, first, second, third, on down forever. Cantor's response is not to argue, it is to build. He takes their list and he constructs, using their own numbers, a brand new number between 0 and 1 that is guaranteed not to be anywhere on their list. He builds it to disagree with their first number in its first decimal place, to disagree with their second number in its second decimal place, to disagree with their third number in its third decimal place, and so on, all the way down. The number he builds differs from every number on the list. In at least one spot, it cannot be the first one, it cannot be the second one, it cannot be any of them, and yet it is a perfectly good real number between 0 and 1. Which means the list was not complete after all. It was missing at least one number, his number. And here is the part that closes the trap. The part that should give you a small cold feeling when you understand it. This works against any list. It does not matter how the person arranged their numbers, how clever their ordering was, how they swore up and down they had captured all of them. You hand Cantor any list whatsoever, and he hands you back a number it missed. There is no list that survives. There is no possible way to put the real numbers in a single infinite sequence, because any sequence you propose can be diagonalized, can be defeated, can be shown to leave something out. The real numbers are not denumerable. They are too many. They overflow every attempt to count them. They are a larger infinity than the whole numbers, and the gap between the two cannot be closed by any trick, any arrangement, any cleverness, because the proof works against all of them at once. That is what was hiding inside a 3-page paper with a boring title in 1874. The first proof that the impossible thing was real. Now, before we go on, I have to correct something, because if I do not, you will carry a misunderstanding into the rest of this, and it will rot everything downstream. You might be thinking that what makes the real numbers bigger is that there are simply more of them packed onto the line, that the fractions leave gaps and the irrationals fill them in, and that filling in the gaps is what gets you to the larger infinity. That is the natural picture, and it is false. And the way it is false is one of the strangest facts in this entire subject. Remember, the fractions, the rational numbers, they are the same size as the whole numbers, Aleph Null, the small infinity. And the fractions are dense. Between any 2 points on the line, no matter how close together you pick them, there are infinitely many fractions. There is no gap anywhere on the line that does not have fractions in it. You cannot find a stretch of the number line, however tiny, that the fractions do not already crowd into. And yet, there are only countably many of them. The small infinity. You can put every last one of them in a list. Density is not the thing. Filling up the line is not the thing. The fractions already do that, in a sense, and they stay small. The thing that makes the real numbers uncountable is subtler and worse. It is that, even though the fractions are everywhere, even though they are dense, they are full of holes, invisible holes, points like the square root of 2, points like pi, points that are not any fraction at all, and there are so unspeakably many of these holes that they outnumber the fractions not by a little, but by an entire order of infinity. The line looks completely full when you put the fractions on it. It is not. It is almost entirely holes. The fractions, all infinity of them, are a scattering of dust on a line that is overwhelmingly made of something else, something uncountable, something that the counting numbers can never reach. If you could throw a dart at the line and hit a truly random point, the probability that you would land on a fraction is 0. Not small. 0. You would land, with certainty, on one of the holes. The thing you thought the line was made of is the rounding error. The thing you never think about is almost the whole of it. That is the kind of result Cantor was producing, one after another, and each one tightened the screw. In 1877 he found another one, and this one disturbed even him. He had been trying to prove something he was sure was true, that a line and a plane must have different numbers of points, that a two-dimensional square must contain more points than a one-dimensional segment, because the square is, well, bigger, it has area, it spreads out in two directions, while the line only goes in one. He set out to prove the obvious, and he proved the opposite. He found a way to pair up every point in a solid square perfectly, one to one, with the points on a single line segment. The square does not have more points than the line. It has exactly as many, and the same holds for a cube, and for a four-dimensional hypercube, and for a space of any number of dimensions you like. Dimension, the thing that seems like it should multiply the number of points, does nothing to the size of the infinity. A line, a plane, a solid, all of space, all the same size. The continuum is the continuum no matter how many directions you let it run. When he had the proof in front of him, he could not quite accept it. He wrote to Dedekind again, and the line he wrote has become the most famous thing he ever said, more famous than any theorem. I see it, he wrote, but I do not believe it. Je le vois, mais je ne le crois pas. He wrote it in French, in the middle of a German letter, as if the result was so strange it needed a different language to hold it. Here is a man, one of the most rigorous thinkers of his century, looking at a proof he himself had constructed, a proof he could not find a single flaw in, and telling his friend that the truth of it would not go down. His own reason had outrun his own belief. He could follow the logic to the conclusion, and he still could not make himself feel that the conclusion was true. I want you to hold that image, because we are going to come back to it. A man who can prove a thing and cannot believe it, because the relationship between what Cantor could prove and what he could believe, between his reason and his conviction, is the hidden engine of his whole tragedy, and it runs in both directions, and by the end, you will not be sure which one was driving. But the dimension result did something else, something with consequences. It landed Cantor's paper on Kronecker's desk again, and this time, Kronecker did not let it slip through. The dimension paper went to Krell's journal in 1878, and Kronecker held it. He sat on it. As a member of the editorial board, he had the power to delay, and he used it. And the paper that should have appeared promptly was stalled long enough that Cantor understood exactly what was being done to him and by whom. He was so enraged and so wounded that he never submitted another paper to Krell's journal again. Think about what that means in practical terms. The most important German mathematics journal of the era, the natural home for his work, the place where he had published the result that started everything, was now closed to him, not by a rejection, not by a fair review, but by one man's quiet decision to make it impossible. He had to take his work elsewhere, to smaller venues, to journals with less reach, and the effect was to push the most consequential mathematics of the century toward the margins of the field, while its author watched. That was the beginning. It got worse, and the worse it got, the more personal it became. Kronecker did not confine himself to editorial maneuvering. He attacked Cantor by name and in public, and the words he used were not the words of academic disagreement. He called Cantor a charlatan. He called him a corrupter of youth, a phrase with a particular venom to it. The same accusation that was once leveled at Socrates, the charge of poisoning the minds of the young with dangerous ideas. He is reported to have said that Cantor's work contained no mathematics at all. I do not know, he said, what predominates in Cantor's theory, philosophy, or theology, but I am sure that there is no mathematics there. Sit with the cruelty of that for a moment. To a man who had devoted his entire life to mathematics, to a man who believed his theorems were as rigorous as anything in the discipline, his former teacher was announcing to the world that the thing he had made was not even mathematics. It was confusion dressed up as proof. It was philosophy and theology, the two words used as insults, the two soft disciplines a real mathematician was supposed to look down on. And Kronecker did the most damaging thing of all, the thing Cantor could never forgive and never recover from. He made sure Cantor would never get to Berlin. Every time a position opened, every time Cantor allowed himself to hope that he might finally leave Halle and take his place among the people he considered his equals, Kronecker was there, at the center of Berlin mathematics, and the door stayed shut. Cantor became convinced, and he was probably right, that Kronecker was personally and deliberately blocking his path, that he was sentenced to spend his career in a provincial university, not because his work was weak, but because the most influential man in his field had decided to ruin him. You were never going to be told this part in school, by the way, because the school version of mathematics is a clean ladder of discoveries, one genius politely handing the torch to the next. The real version is a knife fight in a stairwell. Here is the friction, though, the part where I have to be honest with you, even when honesty complicates the story I am selling. Kronecker was not a villain in a melodrama. He was not stupid. He was not jealous in some petty way. He was not simply cruel for its own sake. He genuinely, deeply, philosophically believed that Cantor's infinities did not exist. He believed mathematics had to be built only from things you could construct in finite steps, and that the moment you started treating completed infinities as real objects, you had left mathematics and entered fantasy. This is a serious position. It did not die with Kronecker. It became the foundation of an entire school of thought called constructivism. And great mathematicians in the 20th century, men like Brouwer, took it up and developed it into something rigorous and respectable. When Kronecker looked at Cantor's work, he was not seeing nonsense out of malice. He was seeing what he sincerely regarded as a catastrophe for the foundations of his discipline, and he was fighting it with everything he had because he thought he was defending mathematics from corruption. The tragedy is not that a bad man attacked a good one. The tragedy is that two serious men held incompatible visions of what mathematics even was, and only one of them held the keys to the kingdom, and he used them. And here is the detail that tells you the war was already lost on the inside, long before Kronecker died. The persecution did not stay outside Cantor's skull. It moved in. In 1884, the year of his first breakdown, Cantor wrote 52 letters to his friend and supporter, Gösta Mittag-Leffler, the Swedish mathematician who had founded the journal Acta Mathematica, and who had been one of Cantor's most loyal champions in Europe. 52 letters in a single year. And Kronecker's name appears in every one of them. Every single letter circles back sooner or later to the same man, the same enemy, the same wound. That is not the correspondence of a mind at peace doing mathematics. That is a man whose persecutor has taken up permanent residence in his head and will not leave. A man who cannot write to a friend about anything at all, without the conversation bending back toward the person who is ruining him. Kronecker did not need to be in the room. He was in Cantor's mind, rent-free, all day, every day, for years. And then the friend flinched too, and that was worse than anything Kronecker ever did. In 1885, Mittag-Leffler, the loyal one, the champion, wrote to Cantor about a new paper Cantor had submitted to Acta Mathematica, work pushing his theory of order types into new and stranger territory. And Mittag-Leffler asked him to withdraw it, not because it was wrong, because it was, in Mittag-Leffler's judgment, too far ahead, too speculative, premature, The kind of thing that would damage Cantor's reputation and the journals if it appeared now, before the world was ready for it. He was trying to protect Cantor. He framed it as a kindness, as advice from a friend who wanted to shield him. And to Cantor, it landed as a knife between the ribs, because it came from inside, from the one person who was supposed to be on his side, telling him to put his work back in the drawer and wait. An open enemy you can fight. You can sharpen yourself against him. But a friend who tells you, gently, for your own good, that your best new ideas are too dangerous to publish, that you should hide them, that the world is not ready, that does something to a person that no enemy can do. Cantor pulled back. He largely stopped publishing major new set theory for years. He turned, more and more, toward theology, toward the Bacon and Shakespeare question, toward anything but the fight he was losing on every front. The man who had cracked infinity went quiet, wounded by an act of friendship, and the silence lasted. But while the war over whether his infinities were allowed to exist raged on, Cantor kept finding more of them. And in 1891, he published a short paper that did two things at once. It gave the clean version of the proof I described earlier, the one where you build a number that disagrees with every number on the list, along the diagonal, which is why it is now called the diagonal argument, and why it is taught, when it is taught at all, as one of the most elegant proofs in all of mathematics. He presented it at the very first meeting of the German Mathematical Society, held in Halle, his own town, in 1891. And in a gesture that tells you something about the man, something that does not fit the legend of the embittered madman, he invited Kronecker to address that same meeting. He tried, even then, to reconcile. The invitation went out. Kronecker did not come. His wife had been badly injured in an accident and would soon die. And Kronecker himself died later that same year. The war ended not with a truce, but with a death. And the man Cantor had spent 15 years fighting was simply gone, and it changed nothing. Because by then, the damage was internal, and the enemy Cantor was really fighting had moved inside. The 1891 paper did a second thing, though, and the second thing is the one that opens the trapdoor under the whole subject. The diagonal argument does not just prove that the real numbers are bigger than the whole numbers. Cantor realized it proves something far more general and far more disturbing. It proves that you can do this trick to any set at all. Here is the move, and it is worth slowing down for, because it is the moment infinity stops being two sizes and becomes an endless tower. Take any collection of things, any set, finite or infinite, it does not matter. Now consider all the possible subsets of that collection, every possible way of choosing some of its members, including choosing none of them and choosing all of them. Mathematicians call this the power set, the set of all subsets, and Cantor proved, with a version of the same diagonal argument, that the power set is always strictly larger than the original set. Always, no matter what you start with. The collection of all the ways to choose from a set is bigger than the set itself, in the precise sense that you can never pair them up one to one. There are always subsets left over, the same way there were always real numbers left off every list. Now watch what that does. Start with the whole numbers, size Aleph null, the smallest infinity. Take its power set. You get something strictly larger. Take the power set of that. You get something larger still, and again, and again. Each time you take the power set, you leap to a strictly bigger infinity. And there is no reason to ever stop. And so there is not just a small infinity and a large one. There is an endless ascending staircase of infinities, each one unreachably larger than the last, going up forever, with no top There is no largest infinity. There cannot be. For any infinity you name, however vast, the set of its subsets is larger, and the set of those subsets is larger than that. On and on, with no ceiling, no final step, no biggest. The tower has no top floor. You can climb it forever, and you will never arrive anywhere, because there is no anywhere to arrive at. The infinities go up without end, and the endlessness of the counting numbers, the thing that as a child terrified you with its bigness, is just the ground floor. That should unsettle you more than the first result did. And if it does not, I have not explained it properly, because the natural human response to learning there are different sizes of infinity is to imagine a kind of ladder with a few rungs, a small infinity and a big one, and maybe a couple in between. And then, at the top of it all, the real infinity, the ultimate one, the biggest possible endlessness, the place where it all finally maxes out. Cantor proved there is no such place. The concept of a biggest infinity is not just unknown, it is incoherent. It leads immediately to contradiction, because whatever you propose is the biggest, its power set is bigger, and your proposal collapses. The thing your mind reaches for when it tries to find the top of infinity is a thing that provably cannot exist. And Cantor, who was by now a deeply religious man, looked at that endless tower with no top, and he did not see a void. He saw God. He decided that the place at the top, the thing the staircase was reaching toward and could never touch, the absolute and final infinity beyond every transfinite number, was not a mathematical object at all, but a theological one. He called it the absolute. He distinguished it carefully from his transfinite numbers, which were real, determinate, mathematical things you could calculate with. The absolute was different. The absolute could not be reached, could not be increased, could not be grasped or determined or written down. And that, to Cantor, was exactly what God was. The transfinite was the creation. The absolute was the creator. And he came to believe, with total sincerity, that the entire structure had been shown to him, that he had not invented the transfinite numbers. He had received them, that he was a messenger. We have to talk about that, because it is the part of the story that the legend turns into madness, the religious mania, the man who thought God was whispering set theory to him. And the truth is more uncomfortable than the legend, because his religious convictions were not the ravings of a broken mind. They were a coherent and seriously argued theology that he developed in correspondence with actual theologians and cardinals of the Catholic Church. And the people he wrote to took him seriously, and some of them agreed with him. We are going to get into exactly what he believed and who he convinced. But first, I have to tell you about the spring of 1884, because that is when the thing the whole legend is built on actually happened. And the date matters, and the timing matters, and almost everyone gets it wrong. In May of 1884, at the age of 39, at the height of his powers, with the diagonal argument still 7 years in his future, George Cantor suffered the first major mental breakdown of his life. It came on suddenly. It lasted somewhat more than a month. It was severe enough to require hospitalization. And when the legend tells you that infinity drove him mad, this is the event it is pointing at. The first crack, the beginning of the end. The story practically writes itself. He stared too long into the abyss of the transfinite. He wrestled with infinities no human mind was built to hold, and something gave way. It is irresistible. It is the kind of thing that feels true. It is also, according to the historians who have actually read the medical records and the letters and the archives, almost certainly false. And the way it is false is going to change how you see everything that follows. The legend that infinity broke Cantor's mind has a specific author. His name was Eric Temple Bell. and in 1937 he published a book called Men of Mathematics that became for decades the most widely read history of the subject in the English language. Generations of people who went on to become mathematicians read it as teenagers and caught the fever from it. It is a wonderful book to read and a terrible book to trust, because Bell was a storyteller first and a historian a distant second. And the story he told about Cantor is a small masterpiece of insinuation. Bell painted a man whose troubles flowed from a Freudian war with his domineering father, whose feud with Kronecker was sharpened. Bell suggested, with an ugly relish, because both men were Jewish, and whose madness was the natural price of staring into the transfinite. The chapter is titled, with Bell's characteristic subtlety, Paradise Lost. The implication is everywhere. He went too far, he saw too much, he paid. Almost none of it survives contact with the actual record. The historian who did the real work, who went into the archives and read the letters and the clinic documents and reconstructed what actually happened, was Joseph Dauben, whose biography of Cantor, published in 1979, is still the definitive account. And Dauben is blunt about Bell. He opens his book by naming Bell directly as the man who popularized the false portrait, the Freudian father, the Jewish feud, the madness born of mathematics. Dauben's verdict, supported by the British historian Ivor Grattan Guinness, who went through the records of the Halle Nerve Clinic himself, is that Cantor suffered from an organic mental illness, what they understood at the time as manic depression, and what we would now call bipolar disorder, and that this illness was endogenous. It came from inside. It was a feature of his biology, his brain chemistry, the same illness that strikes people who have never thought about infinity for a single second of their lives, the same illness that filled the asylums of 19th century Europe, with farmers and clerks and housewives. One of the physicians who examined him later described the condition as a cyclic, manic depression. It was a disease. Cantor had it the way a person has diabetes or epilepsy. He did not catch it from set theory, and the timing proves it if you look honestly. The first breakdown came in 1884. After that breakdown, there is no record of another hospitalization for 15 years. 15 years. If infinity were eating his mind, if the transfinite numbers were the poison, you would expect a steady decline, each new result driving him deeper, the breakdowns clustering around his hardest work. That is not what happened. He had his collapse, he recovered, and he spent a decade and a half doing more mathematics, including the diagonal argument, including the power set theorem, including the most important work of his life, without being hospitalized at all. The breakdowns, when they returned in a pattern that matches the natural cycle of bipolar illness, not the pattern of a man being slowly destroyed by his own ideas. The illness ran on its own clock. The mathematics was not turning the gears. Why does the legend persist? Why, if the historians settled this decades ago, are you still far more likely to have heard the version where infinity drove him mad than the version where a man with a serious psychiatric illness also happened to do mathematics that changed the foundations of the field? And here is where I want you to feel something, because the answer is not innocent. The legend persists because it is comforting. It is comforting in a way that is almost too neat. If Cantor went mad because he looked too far into the infinite, then the infinite is dangerous, and the danger is a kind of cosmic justice, a warning sign posted at the edge of what humans are allowed to know. Do not look too hard at the foundations of reality, or you will be punished. It turns his suffering into a morality tale. It makes the abyss into something that protects itself. That strikes down the people who get too close, and there is a strange comfort in believing the universe has guardrails like that some questions come with a built-in penalty, that the unknowable defends itself. The truth has no such comfort in it. The truth is that a man with an illness that had nothing to do with his work did the greatest mathematics of his century, and the world treated him like a heretic, and the illness and the persecution fed each other, and there was no cosmic justice in any of it, no guardrail, no warning, just a sick man being right and being punished for it at the same time. The infinite did not strike him down. The infinite does not strike anyone down. It does not notice you. That is so much worse than the legend, and we are going to keep finding that this story replaces every comforting version with a colder one, and that this is the pattern, all the way to the bottom. But I have to complicate my own correction now, because if I leave it at the illness was purely biological and the mathematics was irrelevant, I will have told you something almost as misleading as the legend. Because here is the thing the records also show, the detail that does not fit cleanly into either story. When Cantor was in his manic phases, when the illness lifted him into those states of enormous energy and grandiosity and feverish certainty, the thing his mind reached for again and again was always the same. It was not random. It was the mathematics and it was God. And increasingly, it was the two of them fused into a single object, the transfinite numbers and the absolute, and the conviction that he had been chosen to reveal them. The illness did not create his ideas, but it poured fuel on the part of him that was already certain those ideas had a divine source, and in the manic states, that certainty could become total, unshakable. A man on fire with the knowledge that God had shown him the structure of the infinite, and that the men attacking him were not just wrong, but were standing against revelation itself. Dublin makes an argument about this that I find genuinely hard to sit with, and I want to be honest that I do not fully know what to do with it. He suggests that the manic phases may not have only damaged Cantor, they may have helped him. They may have given him the superhuman stamina and the immovable conviction he needed to keep defending a theory that the entire establishment was trying to bury. A more balanced man. A man without that fire might have folded under the pressure Kronecker applied, might have backed down, might have decided the fight was not worth it. Cantor could not back down, partly because the illness made backing down impossible, made the certainty into something that felt like bedrock. The disease that hospitalized him may also be part of why transfinite set theory survived its first decade at all. I do not know how to weigh that. A thing that wounded him may also be a thing that protected his work, the same fire. And now I need to tell you what he actually believed, because the religious dimension of this is usually either mocked or skipped, and both are mistakes. Cantor did not have a vague spirituality. He had a worked-out theology of infinity, and he developed it in writing, in letters, with people who were professionally qualified to push back. The most important of these was a Jesuit, Cardinal Johann Baptist Franzelen, one of the leading Catholic theologians of the day, an advisor on doctrine at the highest levels of the Church. Cantor wrote to him in the 1880s because he was worried about a theological objection to his work. And the objection was a serious one. If you say there are completed infinities other than God, infinities you can do arithmetic with, are you not diminishing God? Are you not setting up rival infinites, lesser gods, an infinity of infinities that competes with the one true infinite? That is close to pantheism, and pantheism is a heresy. And Cantor did not want to be a heretic. He wanted his mathematics to be safe for a believing Christian to hold. He made a distinction, and the distinction is genuinely elegant. There is the transfinite, he said, which is everything in his tower of infinities, all the alephs, all the endless ascending sizes. These are real. but they are created. They are part of the world God made, the way the stars and the numbers and the laws are part of the world God made. They can be increased. Each one has a larger one above it. They are determinate, definite, mathematical. And then there is the absolute, the true infinite, which is God, and which is none of those things. It cannot be increased. It cannot be reached from below by any sequence of the transfinite numbers. It cannot be determined or grasped or made into an object of mathematics, because the moment you could grasp it, it would not be the absolute anymore. The transfinite is the staircase. The absolute is what the staircase reaches toward and can never touch. And it is precisely the unreachability, the fact that no infinity in his tower can ever climb up to it, that makes it divine. Franzolin considered this, and Franzolin, the Vatican theologian, accepted it. He agreed that Cantor's distinction kept the theory clear of pantheism. The transfinite numbers were allowed. Cantor sent material on to others. A neo-scholastic philosopher named Godbelet defended the theory in print, arguing that the transfinite numbers existed in the mind of God, that they had always existed there, eternal, in the divine intellect, and that Cantor had merely discovered what was already in God's thought. Cantor sent work toward Pope Leo XIII himself. He saw the whole project as theological as much as mathematical. And he wrote, in a letter in 1888, a sentence that should make the hair on your neck stand up given everything that was coming. My theory stands as firm as a rock, he wrote. Every arrow directed against it will return quickly to its archer. He believed this not because he had checked the proofs one more time, but because, as he put it, he had followed its roots to the first infallible cause of all created things. He thought he was safe because he thought God was behind him. The theory could not fall because God did not fall. He had staked his certainty not on mathematics, but on the divine, and the cruelty waiting for him. The cruelty none of us would wish on anyone is that there was one piece of his theory, one single question right at the heart of it, that would not behave. That would not yield to the proofs. That refused, year after year, to confirm itself the way the rest of his tower had. He had built the whole staircase. He had named the small infinity and proven the larger one and shown the tower had no top. There was just one thing he could not nail down, and it was the most basic question you could ask about the very first gap in the tower, the gap between the counting numbers and the line. And he was certain, with the certainty of a man who believed God was at his back, that he would prove it. He spent the rest of his life trying. He never did. And the reason he never did is the thing I have been keeping from you, the thing two men would prove decades after his death, the thing that turns this from a tragedy of persecution into something stranger and colder. He did not fail because he was sick. He did not fail because he was not brilliant enough. He failed because the question he was asking is one that cannot be answered, and the universe of mathematics itself will not take a side. The question is called the continuum hypothesis, and you can understand it completely in about 30 seconds, which is part of what makes its fate so disturbing. Cantor had two infinities in hand. The small one, Aleph Null, the size of the counting numbers and the fractions. And the big one, the size of the continuum, the number of points on the line, the size of the real numbers, which he had proven was strictly larger. A natural question presents itself, the most obvious follow-up question imaginable. Is there anything in between? Is there an infinity larger than the counting numbers but smaller than the line? A size that is too big to be listed like the fractions, but not big enough to reach the full continuum. A middle infinity, hiding in the gap. Cantor's answer, his hypothesis, was no. He believed there was nothing in between. He believed the continuum was the very next infinity after Aleph Null, the first step up with no landing in between, so that the size of the line was the second infinity. Aleph 1, the immediate successor of the countable. No middle size, no intermediate infinity. The jump from the counting numbers to the line is a single step, the smallest possible step, with nothing in the gap. That is the continuum hypothesis. There is no set whose size is strictly between the integers and the line, and Cantor was sure it was true, and he set out to prove it, and proving it became the central obsession of the rest of his career. He could not do it, and the way he could not do it has a specific awful texture that the letters preserve. Early in 1884, the same year as his first breakdown, he wrote to colleagues that he had found a proof. He had it. The continuum hypothesis was established. And then, days later, he wrote again to say he had been wrong, and that in fact, he could now prove the opposite, that the hypothesis was false. And then, days after that, a third letter to say that this too was a mistake, that he had proven nothing, that he was exactly where he had started, with the question wide open and no purchase on it anywhere. Proof, disproof, nothing. Inside a single span of days. Imagine the state of a mind doing that. Imagine being certain you have captured the most important result of your life. Then certain you have demolished it. Then waking to find both certainties were phantoms, and the thing is still sitting there, untouched, staring at you. He did this for years. He would think he was close. He would retreat. The continuum hypothesis would not confirm, and it would not deny. It just sat in the center of his theory, like a locked room in a house he had built with his own hands, and he could not find the key, and he could not stop looking for it. You should be feeling something familiar by now, a small echo, and it is deliberate. Remember, I told you to hold on to the image of a man who could prove a thing and could not believe it. With the dimension result, his reason ran ahead of his belief. With the continuum hypothesis, something worse happened. His belief ran ahead of a proof that would never come, because the proof does not exist, and he could not know that. And so he chased it the way you chase something in a dream that stays the same distance away no matter how fast you run. He was not failing at a hard problem. He was failing at an impossible one. And the difference between those two things was invisible to him, and it was invisible to everyone, and it would stay invisible for half a century. The rest of the mathematical world did not yet know it was impossible either, and so the continuum hypothesis did not die with Cantor's failure to prove it. It got promoted. In 1900, the greatest mathematician of the new century, David Hilbert, stood up at the International Congress of Mathematicians in Paris and delivered a lecture that would shape mathematicians for 100 years. He laid out a list of the most important unsolved problems in the field, the problems he believed should guide the work of the coming century. There were 23 of them, and the very first one, problem number 1, at the top of the list, ahead of everything else, was Cantor's continuum hypothesis. The thing Cantor could not prove was now officially the most important open question in mathematics, by the judgment of the man with the most authority to say so. Cantor's obsession had become the discipline's obsession. The locked room was now at the center of everyone's house. That should have been a vindication, and in a way it was, but it came braided together with humiliation, because 4 years later, Cantor's work was nearly destroyed in public, in front of his own daughters. In August of 1904, at the Third International Congress of Mathematicians in Heidelberg, a mathematician named Julius Koenig presented a paper, and the paper claimed to prove that Cantor was wrong. Not wrong about the continuum hypothesis specifically, but wrong about something even more fundamental. the claim that the continuum could be well ordered, which was load-bearing for the whole structure of the alephs. Koenig stood up in front of the assembled mathematical elite of the world and presented what looked like a rigorous disproof of a central pillar of transfinite set theory. It was a sensation. The room understood what it was watching, and Cantor was there, in the audience, with two of his daughters, Else and Anna Marie, watching a man dismantle his life's work in front of everyone who mattered. By the accounts that survive, he was devastated. He took it as a public ruin. He is said to have been thrown into a kind of religious crisis by it, to have demanded of God how this could be allowed to happen, how the theory he believed had been divinely revealed could be exposed as false in front of the world. And then, the next day, it fell apart. Another mathematician, Ernst Zermelo, went through Koenig's proof and found the flaw. Koenig had relied on a result from someone else's doctoral thesis, a theorem that turned out not to be as generally true as its author had claimed. And once you removed that faulty piece, Koenig's disproof collapsed entirely. It proved nothing. Within a day, the great public refutation of Cantor's theory had become a footnote, a mistake, a thing that did not work. The following year, the faulty thesis result was formally corrected and Koenig's claim was withdrawn. Cantor's theory had not been disproven. It had survived, and the whole episode backfired in the most productive way imaginable, because in the course of cleaning up Koenig's mess, Zermelo was driven to prove the well-ordering theorem properly and then to build the first real axiom system for set theory, the foundation that the entire subject still rests on today. The attempt to destroy Cantor's paradise ended up reinforcing its foundations. There is a piece of that repair that I skipped past, and I skipped it on purpose because it deserves its own moment, because it is the place where the line between proving and believing, the line this whole story keeps erasing, gets erased again, right at the foundation of the subject. When Zermelo proved that the continuum could be well ordered, when he showed that Cantor's infinities could be lined up in a neat sequence after all, he had to use something, a principle, an assumption he had to drag out into the open and write down, because the proof did not work without it. He called it the axiom of choice, and the moment he stated it, mathematics went to war with itself all over again. And this time, the war was not about Cantor personally. It was about whether you are allowed to believe in things you cannot build. Here is what the axiom of choice says, and I want you to notice how harmless it sounds. Suppose you have a collection of boxes, and every box has at least one thing in it. The axiom of choice says you can reach into all the boxes at once and pull out exactly one thing from each, forming a new collection made of your selections. That is it. For a handful of boxes, this is obviously fine. You just point at one thing in each box and you are done. Even for infinitely many boxes, if there is a rule that tells you which thing to grab, say always take the smallest number in the box, you are still fine, because the rule does the choosing for you. But the axiom of choice claims something much stranger. It claims that even when you have infinitely many boxes, and there is no rule, no method, no describable way to decide what to take from each one, you can still make all the choices at once, all infinity of them, and the resulting collection exists. It exists even though you can never say what is in it. It exists even though no human being and no machine could ever write it down or describe it or construct it in finite steps. You assert that the selection is there, complete and finished, while admitting you can never exhibit a single concrete version of it. To Kronecker, that would have been the final nightmare, the purest possible example of the rot he spent his life fighting, an object asserted into existence by faith, with no construction behind it. And Kronecker was dead. But his suspicion was not, and it rose up now in a new generation. The fiercest objections came from France, from three of the finest analysts alive, Émile Borel, René Baer, and Henri Lebesgue. They exchanged a famous series of letters in 1905 arguing about exactly this. And their unease was Kroneker's unease wearing French clothes. How can you claim a thing exists, they asked, if you can never name it, never define it, never produce it? To assert the existence of a choice you cannot describe is not a mathematical act. It is an act of faith. It is belief without proof, smuggled into the heart of mathematics and dressed up as an axiom. And here is the part that should land on you with some weight, because it ties the knot this whole story has been tying. To put Cantor's infinities in order, to make the Tower of Alephs behave, to prove the basic structural facts that the whole theory needs in order to function, mathematics found that it required the axiom of choice. The machinery for organizing the infinite rested on an assumption you can only take on faith and can never construct. The tools needed to handle Cantor's discovery were themselves articles of belief. You could not even arrange his infinities tidily without committing to the existence of objects no one could ever build or see. The proving and the believing were not in separate rooms. They were welded together at the foundation, and you could not pull them apart without the building falling down. The axiom of choice also produces things that sound like madness and are not. In 1924, two mathematicians, Stefan Banach and Alfred Tarski, used it to prove that you can take a solid ball, cut it into a finite number of pieces. Just 5 will do. Move those pieces around rigidly, without stretching or bending them, and reassemble them into 2 solid balls, each the exact same size as the one you started with. 1 ball becomes 2, out of nothing, with no material added, by pure rearrangement. It is called the Banach-Tarski paradox, and it is not a trick or an error. It is a theorem. It follows from the axiom of choice. The catch is that the pieces you cut the ball into are not shapes you could ever actually cut, not blobs or chunks, but infinitely scattered clouds of points, so pathological that they have no definable volume at all. Objects that can only exist because the axiom of choice reaches into infinitely many boxes and pulls out a selection no one can describe. Mathematicians looked at a theorem that says you can double a ball from nothing, and rather than abandon the axiom of choice, they kept the axiom and accepted the doubled ball, because choice had become too useful to give up. Almost all of modern mathematics quietly depends on it. To save the working tools, the field swallowed a result that violates every physical intuition you have, and it swallowed it on purpose, with full knowledge of how strange it was. And then, decades later, the axiom of choice met the same fate as the continuum hypothesis by the same 2 men. Gödel showed you cannot disprove it from the other axioms. Cohen showed you cannot prove it from them either. The axiom of choice is independent, undecidable. One more question the foundations of mathematics refuse to settle. One more place where the subject hands you the decision and tells you to believe whatever you can live with. You can build a mathematics with choice and a mathematics without it, both consistent, both legitimate, and nothing underneath can tell you which one is true. Cantor did not live to see any of this resolved, because none of it ever was resolved, but it was his infinities that forced the question into existence. It was his tower that could not be put in order without an act of faith. The man Kronecker accused of smuggling theology into mathematics had, it turned out, found the exact place where mathematics runs out of proof and has nothing left to stand on but belief. And that place was not at the edge of the subject, it was at the center of it, holding everything up. But think about what the whole Heidelberg ordeal must have done to a man already living with a cyclic illness, already convinced his theory came from God, already worn down by decades of chronica, to stand in a room and watch your work apparently destroyed, to fall into despair and religious crisis, and then to have it restored the next morning. The relief and the whiplash of that, the illness fed on episodes like this. The hospitalizations, which had been rare, began to come more often after 1904. Every 2 or 3 years, the pattern tightening as he aged. The same year as the Koenig humiliation. By the way, the Royal Society in London awarded him the Sylvester Medal, its highest honour for mathematical research, only the second time it had ever been given. Vindication and catastrophe in the same 12 months. That was the rhythm of his life now. The world told him he was a genius and told him he was a charlatan, sometimes in the same season, and his own mind kept lifting him up and dropping him. And underneath all of it, the continuum hypothesis sat, unsolved, refusing him the one thing he wanted most and could not have. And then the foundations themselves started to crack, and the cracks came from inside Cantor's own work. And this is the part where the universe of mathematics begins to look less like a building and more like something with a will of its own. Cantor had already noticed, before anyone else, that his tower of infinities contained a trap. If there is no largest infinity, if you can always take the power set and get something bigger, then what about the set of everything? The set of all sets, the collection that contains absolutely every set there is. How big is that? It would have to be the biggest infinity of all, because it contains everything. But there is no biggest infinity. Its own power set would have to be bigger than it, and yet its power set is a collection of sets, so it is already inside the set of all sets, so it cannot be bigger. The thing both has to be the largest infinity and cannot be the largest infinity. It is a contradiction. It breaks. Cantor found this himself around 1897, and in a letter to Dedekind in 1899, he described such collections with a haunting phrase. He called them inconsistent, absolutely infinite aggregates, collections so large that to assume they exist as completed objects produces contradiction. He had found the edge of his own paradise, the place where it tears. He thought he could quarantine the problem by declaring those monstrous collections to be absolute, to be off-limits, part of God's domain, rather than the mathematicians. But the crack would not stay quarantined. In 1901, a young British philosopher named Bertrand Russell found a version of the same paradox, so simple and so sharp that it could not be waved away. Consider the set of all sets that do not contain themselves. Does it contain itself? If it does, then by its own definition it must not. If it does not, then by its own definition it must. Either answer contradicts itself, and this was not some exotic monster like the set of all sets. It was built from the most basic, innocent-looking operations in all of set theory, the operations everyone used every day without thinking. Russell's paradox showed that the naive idea of a set, the idea Cantor's whole edifice and indeed all of mathematics had been resting on, was logically broken. You could derive a contradiction from it in 3 lines. The foundations of mathematics were on fire. This is what came to be called the foundational crisis, and Cantor's infinities were sitting at the dead center of it. The most basic concept in the subject, the set, the simple idea of a collection of things, had turned out to harbor contradictions, and the contradictions emerged precisely when you let collections get large, in the way Cantor had taught everyone to let them get large. The reactions were ferocious, and they tell you how high the stakes felt. Henri Poincaré, one of the towering figures of the age, called set theory a disease and predicted that mathematics would one day be cured of it, that future generations would look back on the whole Cantorian episode as a sickness the field had to recover from. Later, Ludwig Wittgenstein would call set theory utter nonsense, laughable, wrong, and would lament that mathematics had been ridden through and through with what he called the pernicious idioms of set theory. The idea that a line is composed of points, he said, the idea Cantor had made the foundation of everything, was a confusion. A line is a law, Wittgenstein wrote, and is not composed of anything at all. The most basic picture in Cantor's work, the line as a vast collection of individual points, was being called a category mistake by one of the most important philosophers of the century. And against all of that stood Hilbert, who refused to give up the infinities even with the foundations burning. He believed the crisis could be repaired, that the paradoxes could be walled off with the right axioms, that the tower could be saved. And in 1925, he gave it the line that became its banner, the line that gets quoted whenever anyone defends Cantor against the people who wanted his work erased. No one, Hilbert declared, shall expel us from the paradise that Cantor has created for us, the paradise. The same word Bell would later use to title the chapter about Cantor's madness, but Hilbert meant it without irony. A paradise, a place of infinite riches that the field had been given and would not surrender, whatever the cost, whatever the paradoxes, whatever it had done to the man who built it. Cantor did not live to see whether the paradise could be saved. He was sliding now into the final phase, and the continuum hypothesis was still open. And he was about to spend his last years in and out of the clinic in Halle, an old man whose work was simultaneously the foundation of the future and a scandal the establishment could not digest. But the question he could not answer was about to get a different kind of answer than anyone expected. Not the answer he wanted, not even an answer in the shape that he, or Hilbert, or anyone thought an answer had to take. Something stranger was waiting, decades down the line, and when it finally came, it would prove that Cantor's failure had never been a failure at all. I want to slow down here and stay with the man for a while, because the last stretch of his life is usually compressed into a single sentence. He died in an asylum, and that sentence does a violence to what actually happened. The decline was long, and it was human, and it had a particular shape, and the shape tells you something. The breakdowns were coming more often now, and between them, he was not the figure you might imagine. He was not raving about infinity. In the periods when the illness had hold of him, his mind turned more and more to things that had nothing to do with mathematics at all. And the most persistent of these was a conviction that Francis Bacon had secretly written the plays attributed to William Shakespeare. This was not a passing fancy. He pursued it with the same ferocious energy he had once aimed at the transfinite. He studied Elizabethan literature. He published pamphlets on it at his own expense, 2 of them in the 1890s, arguing the Baconian theory in dead earnest. He gave a public lecture on the Bacon-Shakespeare question, and the detail that breaks my heart every time I read it is what happened during one of those lectures. On the 16th of December, 1899, while Cantor was delivering a lecture on the Bacon-Shakespeare theory, his youngest son, Rudolph, died. The boy was 13. Cantor had 6 children, and Rudolph was the baby, born in 1886, and he died suddenly while his father was off in public chasing a literary obsession that everyone around him could see was a symptom. Cantor never fully recovered from that death. He connected it in his own mind to everything else, to the persecution, to the failures, to the sense that he was a man marked for suffering. There were other obsessions in those years, stranger ones. he published a pamphlet under a pseudonym arguing a peculiar theory about the parentage of Christ. He wrote increasingly to theologians rather than mathematicians. The man who had cracked the structure of infinity was spending his energy on Elizabethan authorship disputes and religious speculation. And to the people watching, this looked like the mind going, the great instrument detuning itself. And in a sense, it was. But I have to flag something, because the legend likes to embroider this part with claims that do not hold up. You will find sources that tell you Cantor was involved with secret societies, with Rosicrucians or Freemasons, that his religious mania had an occult dimension. The serious scholarship does not support that, and I am not going to repeat it as if it were established, because this story does not need embellishment. The plain facts are strange enough. A genius in decline, chasing Bacon through Shakespeare, burying a son, writing to cardinals, sliding by degrees toward the clinic that would hold him at the end. And the end was grim in a way that had nothing to do with the romance of the mad genius and everything to do with history grinding an old man down. Cantor retired from his professorship in 1913. He was 68. And then the First World War came, and Germany began to starve. The British naval blockade and the collapse of the food supply meant that an old retired professor on a fixed income in a provincial town went hungry like millions of others, and Cantor, never wealthy, because Halle had never paid him what Berlin would have, became thin and weak and sick. A celebration that had been planned for his 70th birthday in 1915 was cancelled because of the war. There was no money and no food and no mood for honouring anyone. He entered the Halle Nerve Clinic for the last time in June of 1917, and from there he wrote letters to his wife, asking again and again to be allowed to come home. He did not come home. On the 6th of January, 1918, he died there of a heart attack. Suddenly, the historian Grattan Guinness, who read the records, put it plainly. The war caused a shortage of food, and Cantor became thinner and prey to hunger as well as to fatigue and illness. And then he died. There was no infinity in the room. There was a hungry old man in a clinic in the third winter of a catastrophic war, dying the way the century was teaching everyone to die, anonymously and from privation, while the world was busy with larger slaughters. Now hold that image, the hungry old man, against what his work was about to become, because the contrast is the whole point, and it is almost unbearable. Within a few decades of that lonely death, the diagonal argument, the little 3-page trick Cantor had used to prove the line was uncountable, would turn out to be one of the most far-reaching and dangerous ideas in the history of human thought, and it would be used to prove things about the limits of knowledge itself that make the original result look almost gentle. Here is what I mean, and this is the escalation. This is where the stakes climb out of the 19th century and into the foundations of everything. The diagonal move, at its core, is a method for showing that a system cannot capture something that it seems like it ought to capture. You have a list that claims to be complete, and you build out of the list's own contents a thing the list cannot contain. That is the shape of the argument. And in the 1930s, two of the most important results in the history of logic were proven using exactly that shape, aimed not at infinity, but at the power of mathematics and machines to know things. The first was Kurt Gödel in 1931. Gödel was trying to answer a dream of Hilbert's, the dream that mathematics could be made complete and certain, that you could write down a finite set of axioms from which every true statement could in principle be proven. A system with no gaps and no contradictions. The paradise made safe forever. Gödel proved this is impossible. He proved that any consistent system of axioms, rich enough to describe ordinary arithmetic, must contain true statements that it cannot prove. There will always be truths the system cannot reach. And the way he proved it was a diagonal argument. He found a way to make a mathematical statement that in effect talks about itself. That says of itself, this statement cannot be proven in this system. And then he used the diagonal structure to show that if the system is consistent, that statement is both true and unprovable. The same move Cantor used to escape every list, Gödel used to escape every proof system. Mathematics, it turned out, cannot fully capture itself. There is always something on the diagonal, always a truth that slips past the net. The second was Alan Turing in 1936, and he used the same weapon on machines. Turing was asking whether there could be a general procedure, a mechanical method, an algorithm that could decide whether any given computation would ever halt or would run forever. He proved there cannot be. No machine can solve the halting problem for all machines. And his proof was, once again, a diagonal argument. Assume the deciding machine exists, then build, out of its own behavior, a case it cannot decide. The thing it cannot handle is constructed from the thing itself, exactly as Cantor's missing real number was constructed from the list that was supposed to contain it. The entire theory of computation, the reason your computer can do some things and provably can never do others, rests on a diagonal argument descended directly from the one Cantor invented to count the points on a line. Every limit on what software can ever do traces back in its deepest logic to a hungry old man's 3-page paper. That is the afterlife of the idea. Cantor reached for infinity and pulled out a method for finding the boundaries of knowledge itself. And he did not live to see what it would become. He thought he was mapping the sizes of the endless. He was actually building the instrument that would prove again and again, in domain after domain, that there are truths no system can reach and questions no machine can answer. The diagonal does not just separate the small infinity from the large one. It is the universe's way of telling every formal system you do not contain everything, and you never will. And here is the thing you missed. Built out of your own pieces, there is something almost alive in how reliably it works. How it turns any system's completeness against itself. How whatever you build to capture the truth, the diagonal walks out through a gap you did not know was there. And the Tower of Infinities itself, once people followed it upward, turned out to contain regions you cannot get to. This is one of the strangest things in all of mathematics, and almost nobody outside the field has heard of it. Some of the infinities in Cantor's staircase are what mathematicians call inaccessible. An inaccessible cardinal is an infinity so large that you cannot reach it from below by any of the operations of ordinary set theory. You cannot get to it by taking power sets of smaller infinities. You cannot get to it by adding up smaller infinities, no matter how many of them you combine, no matter how you stack them. It sits above everything you can construct from beneath it, unreachable, and its existence cannot even be proven from the standard axioms. To have these enormous infinities in your mathematics at all, you have to simply assume they are there, reach up, and posit them, because you can never climb to them. There are sizes of infinity that the machinery of mathematics cannot build, cannot approach, cannot verify, can only assume. Floors in the tower with no staircase leading up to them. You know they would have to be there, far above, if the building keeps going. You can never reach them. You can only believe in them. I keep coming back to the word believe, and you should notice that I keep coming back to it, because it is the hinge of this entire story. Cantor proved the line was uncountable and then could not believe it. He believed the continuum hypothesis and could not prove it. He believed God had revealed his theory and staked his sanity on it. And here at the top of his tower are infinities you cannot reach by proof, but can only take on faith that they exist. The boundary between proving and believing, which is supposed to be the bright, clean line that separates mathematics from religion, that separates Cantor the rigorous logician from Cantor the man writing to cardinals about the absolute, turns out to run right through the middle of mathematics itself. There are mathematical objects you can only believe in. There are mathematical truths you can never prove. The thing Kronecker accused him of, smuggling theology into mathematics, turned out to be not a crime Cantor committed, but a feature of the subject he had uncovered. The faith was not contamination. The faith was load-bearing. Which brings us finally to the continuum hypothesis, and to the answer that is not an answer, the resolution Cantor went to his grave without. The thing two men proved decades after the hungry winter of 1918. Because by now you can feel it coming, the way I promised you would. You can feel that a question sitting at the foundation of a subject riddled with unreachable objects and unprovable truths. A question that resisted the greatest mind of his generation through proof and disproof and proof again. A question Hilbert placed first among all the problems of the century is not going to turn out to have a clean yes or a clean no waiting at the end of a long enough calculation. You can feel that the reason Cantor could not settle it was not a flaw in Cantor. It was something about the question. And you are right. It is worse than you think. It is always worse than you think. That is the only law this story obeys. The first half of the answer arrived in 1938, 20 years after Cantor died, from the same man who had just shown that mathematics could not prove all its own truths. Kurt Gödel turned his attention to the continuum hypothesis, and he proved something precise and strange. He proved that you cannot disprove it. He built, inside the standard axioms of set theory, a kind of minimal, stripped-down model of the mathematical universe, a carefully constructed inner world containing only the sets you are absolutely forced to admit exist, and nothing extra, nothing speculative. He called it the constructible universe. And he showed that inside that lean, disciplined universe, the continuum hypothesis is true. There is no middle infinity in there. The line is the very next size after the counting numbers, exactly as Cantor believed. What that means is subtle, and you have to hold it carefully. Gödel had not proven the continuum hypothesis was true. He had proven that the standard axioms of mathematics can never prove it false. Because if the axioms could prove it false, then it would have to be false in every model of those axioms. And Gödel had just built a model where it is true. That means the axioms cannot rule it out. Cantor's hypothesis is safe from disproof. Forever. No one will ever derive a contradiction from assuming it. After 50 years, that was the first half of the verdict. You cannot prove Cantor wrong. For 25 more years, that is where it sat. And many mathematicians assumed the other half would come eventually. That someone would complete Gödel's work by proving the hypothesis true, finishing the job, closing the room. Hilbert's first problem would finally be solved in Cantor's favor, vindicating the dead man completely. The expectation was that the answer was yes, and it was only a matter of time before someone proved it. The other half came in 1963, and it did not complete Gödel's work. It detonated it. A young American mathematician named Paul Cohen, who was not even a specialist in set theory, invented an entirely new technique to attack the problem. A method so sweeping and so original that it reshaped the whole field. A method called forcing. And with it, Cohen proved the mirror image of Gödel's result. He proved that you cannot prove the continuum hypothesis either. He built a model of the standard axioms in which the hypothesis is false, in which there is a middle infinity, a size strictly between the counting numbers and the line, a model that obeys every axiom of standard mathematics, breaks none of the rules, contains no contradiction, and in which Cantor's hypothesis simply does not hold. Put the two results together and feel the floor go. Gödel built a consistent mathematical universe where the continuum hypothesis is true. Cohen built a consistent mathematical universe where it is false. Both universes obey exactly the same axioms, the same foundational rules that all of ordinary mathematics runs on. The system mathematicians call ZFC, Zermelo's axioms with the axiom of choice, the bedrock under essentially everything. And in one of these equally valid universes, the answer is yes, and in the other, the answer is no. And nothing in the axioms can tell you which one is the real one. The continuum hypothesis is independent of the foundations of mathematics. It is undecidable. The axioms do not contain the answer. They are compatible with both answers. You can add the hypothesis to mathematics as a new rule, and everything stays consistent. You can add its exact opposite, and everything stays equally consistent. Mathematics does not merely fail to know the answer. Mathematics does not have an answer. The question of how many points lie between the integers and the line, the question Cantor broke himself on, the first problem on Hilbert's list, is not unsolved. It is unsolvable in the deepest possible sense, the sense in which there is no fact buried in the axioms waiting to be dug out, because the axioms are silent, and the silence is permanent. Cohen won the Fields Medal for this in 1966, the highest honor in mathematics, and it remains the only Fields Medal ever awarded for work in pure logic. The thing he was honored for is the proof that the discipline's most famous question has no answer that the discipline can give. Think about the shape of that. The greatest prize in mathematics, given for demonstrating the limits of mathematics. The diagonal coming home one final time. The method that escapes every system used to show that the system escapes itself, even here, at the question that started it all. Now, I have to be careful and honest with you, because this is exactly the place where a lazy version of this story would overreach, and you would be right to fact-check me. And the truth is more interesting than the overreach anyway. Independence does not mean every mathematician threw up their hands and agreed. The question is meaningless. It opened the deepest split in the philosophy of mathematics that exists today, and the split is real and live and unresolved, and serious people sit on both sides of it. On one side are the mathematicians who think independence is the final word. The continuum hypothesis, they say, is simply not a definite question. There is no fact of the matter about how many points are on the line. In the same way there is no fact of the matter about whether the bishop in chess is morally superior to the knight. The axioms are the rules of the game. And within the rules, the question has no answer, and there is nothing outside the rules to appeal to. The question feels like it should have an answer because of the words we use to phrase it, but the feeling is an illusion. The line does not have a definite number of points. It never did. The question was malformed from the start, and Cantor spent his life and his health chasing a fact that was never there. On the other side, and this is the side that should unsettle you more, are the mathematicians who think the question absolutely does have an answer, and that our current axioms are simply too weak to see it. This was Gödel's own view, and he held it to the end of his life. Gödel was a Platonist. He believed mathematical objects are real, that the universe of sets exists independently of us, out there, definite, and that the continuum either has a middle infinity or it does not. As a matter of fact, regardless of what our puny axiom systems can prove. On this view, the independence result does not show the question is meaningless. It shows that ZFC is an incomplete description of a reality that is fully determinate. The line has an exact number of points. We just cannot see it from where we are standing, with the axioms we currently have, and we need to find new ones, deeper truths about sets. That would settle it. And mathematicians have spent the decades since Cohen doing exactly that, searching for new axioms, climbing toward those unreachable cardinals, trying to find a vantage point high enough in the tower to look down and finally see whether there is anything in the gap. The most prominent of these programs, pursued for decades by the logician Hugh Wooden and others, has produced extraordinary mathematics and has not settled the question. And the people pursuing it do not agree among themselves about what their own results mean. Here is where it actually stands, and I am not going to pretend it is cleaner than it is, because the lack of cleanliness is the point. We have a theorem, hard and certain, that the standard axioms of mathematics cannot answer the continuum hypothesis. That is not in dispute. It is as solid as Cantor's original proof. And then we have a philosophical abyss that the theorem opened and cannot close, a genuine and unresolved disagreement about whether the question has a true answer we cannot reach or no answer at all. The mathematicians cannot tell you which. The logicians cannot tell you which. The people who have given their entire careers to this single question stand at the edge of it and disagree about whether there is a bottom. The authority you would want to appeal to, the community of experts who are supposed to know, does not know, and more than that, does not agree on whether the thing is knowable. There is no one to ask. There is no answer in the book. There may be no book. And that is the inheritance Cantor left, the thing waiting at the end of the staircase he built. He went looking for the structure of infinity, and he found that the most basic question about the most basic object, how many points are on a line, leads to a place where mathematics goes quiet and the experts fall silent, and the question hangs there with no one able to say whether it even has an answer. He thought God had shown him the transfinite. Maybe what God actually showed him, if you want to think about it that way, was the exact location of the edge of the knowable, the precise point where the foundations of certainty run out. He spent his life trying to cross that edge, not knowing it was an edge, thinking it was just a hard problem on the other side of which lay the proof he deserved. There was no other side. I want to bring this all the way home now, because it would be easy to let the continuum hypothesis stay where it is comfortable, up in the rafters of pure mathematics, a puzzle for logicians, something that does not touch you. It touches you. Let me show you how, and I'm going to be careful and honest about exactly how far the touch reaches, because the honest version is more disturbing than any exaggeration I could invent. Start with the line again. Not a metaphor, an actual line, the edge of the desk in front of you, the path the thrown ball traces through the air, the distance from where you are sitting to the far wall. Physics describes all of it. Every motion, every position, every interval of space, and every interval of time, using the real numbers. The continuum. When a physicist writes down where a particle is, the coordinate is a real number. When the equations of motion run forward, time is a real variable flowing along the same continuum. Cantor proved was uncountable. The entire mathematical machinery of physics, from Newton to Einstein to quantum field theory, is built on top of the real number line. The object you now know contains a question about its own size that mathematics cannot answer. Every measurement you have ever made, every speed, every temperature, every length, was a claim about a point on a continuum whose deepest structure is formally undecidable. The ground that all of physics stands on has a question mark carved into its foundation that no proof can ever erase, and physics simply builds on top of it anyway, because it has to, because the continuum is the only tool that works, and you do not get to refuse the flaw just because no one can tell you how many points it has. Now I have to be straight with you about the limits of this, because there is a version of this story that overreaches here and tells you that physical reality itself is undecidable, that the universe cannot make up its mind, and that is further than the evidence goes, and you deserve the real boundary. We do not actually know that space and time are continuous all the way down. At the smallest scales, near what is called the Planck length, a distance so small that the numbers stop meaning anything you can picture. Some of our best attempts at a theory of quantum gravity suggest that the smooth continuum might break down, that space might be grainy, discrete, made of finite pieces, in which case the line in physics would be an approximation, a useful fiction laid over something pixelated underneath. We do not know. We cannot currently probe anything close to that scale. So I am not going to tell you that the undecidability of the continuum is a physical fact about your universe, because no one knows whether your universe even has a continuum in it at the bottom. But look at what that leaves you with, because it is somehow worse than the overreach. Either space and time really are continuous, in which case the fabric of physical reality is woven from an object whose own size is a question mathematics has proven it cannot answer, and you live inside that unanswerable thing, and you move through it, and you measure it every day with rulers and clocks that quietly assume an answer no one can justify. Or space and time are not continuous, in which case the most successful description of reality ever produced, the continuum that every equation of physics is written on, is a fiction, a smooth lie told over a grainy truth. And we have been doing physics for 300 years on a foundation we cannot even confirm is there. Those are your options. A real continuum with an unanswerable question at its heart, or a continuum that is not real at all. There is no third door where everything is fine, and the line is just the simple, solid, fully knowable thing you assumed it was when you were a child drawing it with a ruler. That child's line is gone. It was the first casualty. Cantor killed it in 1874, and almost no one noticed the body. And here is the part that I genuinely do not know how to settle in my own head, the part I have been circling this whole time. Remember the two camps, the mathematicians who say the continuum hypothesis has no answer, and the ones who say it has an answer we cannot reach. Notice what they share, the thing underneath their disagreement, because it is the most uncomfortable thing in this entire story. Both camps agree that the question is beyond the reach of proof. Both agree that no derivation from the foundations of mathematics will ever settle it. They only disagree about whether there is a truth sitting out there, beyond the reach of proof, in some realm of mathematical fact we can believe in, but never demonstrate. One camp says there is nothing out there. The other camp says there is something out there, real and definite, that we can approach only by faith in axioms we cannot prove, by reaching upward toward infinities we can never climb to. And that second camp, the Platonists, the ones who believe in a determinate mathematical reality beyond the limits of proof, includes some of the most rigorous logicians who have ever lived. Gödel chief among them, the man who proved the limits of proof, spent the rest of his life believing in truths beyond those limits, which means the line Kronecker drew, the line everyone draws, between the mathematician who proves and the mystic who believes, between Cantor the rigorous logician and Cantor the man writing to cardinals about the absolute infinite that the human mind can never grasp. That line does not hold. It was never real. At the deepest level of the most rigorous subject human beings have ever built, You arrive at questions where proof gives out, and all you have left is what you are willing to believe. Cantor believed there was no middle infinity. He believed it on faith because he could not prove it, and we now know he could never have proven it. And we also know he could never have been proven wrong. He was, in the most precise sense, neither right nor refutable. He spent his life and his health, and a good portion of his sanity, defending a proposition that mathematics has since certified can be believed or denied with equal consistency, forever, by anyone, with no possibility of resolution. He was not deluded to believe it. The Platonists believe it, or its opposite to this day, in good standing, with no shame. He was just early. He reached the edge of the knowable before anyone had drawn the map that showed it was an edge, and he stood there pounding on it. And from the outside, it looked like a man going mad against a problem. And from the inside, it must have felt like the one thing God had shown him was the one thing God would not let him prove. I told you at the start that the comforting version of his story, the one where infinity drove him mad, is false, and that the truth is colder. Here is the cold truth, assembled now, all of it. A man with an illness he did not choose and did not cause, an illness that would have come for him whether he ever thought about a number in his life, looked at the most ordinary object in mathematics and saw that it was bottomless. He proved there are different sizes of infinity, and he was right. And it is still true. He proved there is no largest infinity, and he was right. And it is still true. He built a staircase of endlessness that goes up forever with floors no one can climb to. And it is still there, exactly as he described it. And at the very first step of that staircase, in the gap between the counting numbers and the line, he asked the simplest possible question, and the question had no answer. And it has no answer now, and it will have no answer when the last human being who ever cares about it is dead. He gave everything he had to that gap. The world called him a charlatan for the parts he got right, and called him mad for the part that was actually unanswerable. And he died hungry in a clinic in the winter of a war, writing letters asking to come home. And the gap is still open. It will always be open. That is not a tragedy that resolves. That is just where the story stops. Because that is where the man stopped, and the question did not stop with him. Go back, one last time, to the sliver, the numbers between 0 and 1. That little nothing of a gap on the number line, the part you would never bother to measure. You know now that it holds more numbers than all of counting infinity, an entire, larger order of endlessness packed into a space you could cover with your thumb. And you know now that somewhere in the relationship between that sliver and the counting numbers below it, in the question of whether anything lives in the space between them, there is a fact that is not a fact, an answer that is not there, a silence that mathematics has proven it will keep forever. Cantor heard that silence, and he could not stop listening to it, and he decided it was the voice of God, the absolute that cannot be reached or grasped or determined, the infinite beyond all the infinities he could prove. The official story says that was the madness talking. But the absolute, the way he defined it, was exactly this: something real that the mind reaches toward and can never grasp, something true that can never be determined, something that lies forever beyond the last thing you are able to prove. He gave that a name and called it God, and they put him in an asylum for the parts of his work they could not stand. And then, decades after he was in the ground, mathematics proved that the thing he spent his life reaching for really is beyond the reach of proof, really cannot be grasped or determined, really does lie forever past the edge of what can be demonstrated. Sitting there in the gap in the line, in the sliver under your thumb, definite or empty, no one will ever be able to say. He was not wrong about where the edge of the knowable was. He found it before anyone. He just could not tell, standing there at the edge, whether he was looking at the limits of mathematics or the face of God. And the worst thing this story has to teach you, the thing I still do not know how to carry, is that nobody since has been able to tell either. The line is still there. The gap is still open. And whatever is in it or is not in it has never said a word.